Just what does inverse square mean? What types of physical phenomena does it apply to? And what do I even mean by weakens or decays or fades? Let me start with the last two of those questions and then go to the first. We're interested in three types of physical phenomenon. The first you might call radiation. For example, the sun. It is a mass of incandescent gas and a deadly laser. Basically, it's a ball that shoots out photons in all directions, just pew, pew, pew. It just scatters them in all directions, and on average, it sends them out at a certain frequency, a certain number per second per surface area kind of thing. And those photons, they don't degrade, they don't have an expiration time, they don't cool down, they don't disappear. Until they hit something or bounce off something, they just keep going, and if they never hit anything, they go until the end of time. But look at the planet Mercury, it's basically on fire, and Earth is comfortably toasty, I'd say. And then go out to Neptune and it's like, would you like ice or more ice? So if the photons that are shot out by the sun never degrade, they never go away until they hit something, all the way out to Neptune, they're exactly the same until they hit Neptune. Why is Neptune cold and Mercury hot? And another would be actual radiation, such as nuclear waste. Put your little Geiger counter next to it and it goes crazy and pull it away and it's barely anything. So this is something that decays, that gets weaker with distance, is anything that shoots out this stuff in all directions. We'll call those radiant sources. Another is expansive. Expansion, something like an explosion. If you have a bomb that goes off, there's going to be a shockwave of air and heat and shrapnel flying, and similar to radiation, the shrapnel flying would be more like the radiation, but the shockwave, the heat, it starts in the center and it expands and it spreads. It's not being radiated, it's not being shot out, it was generated and it is expanding outward. And just like before, if you're standing right next to the explosion, you have a problem. And if you're standing very far away from the explosion, you just go, wait, what was that? Why is it weaker at a greater distance? And there's one more kind. We'll just say force field. Stuff like gravity, magnetism, electric fields. Force field because they're forces, they exert forces, and they are represented by fields, not the Star Trek kind. Here is a magnet. Here is a nail that is attracted to this magnet. I'm holding this magnet, and it's not picking up the nail. And I move it closer and closer, and all of a sudden, out of absolutely nowhere, it just says, hey, now's the time to pick it up. It suddenly remembers it's a magnet. Why is there such a drastic point at which that happens? Why does it happen at all? So that's the last two questions answered. What does it apply to and what does it mean? Now, let's do what it is. What is inverse square? It's all about the surface area of spheres. So first, imagine that this is actually a sphere. You know, it's a goofy balloon shape, but I did not want to spend $50 on props. So let's say that this is a sphere. Inverse square says that as you get further away from something, from one of these things that I erased and I'm pointing to anyway, as you get further away, it gets weaker. The center of the balloon is the thing. It's the explosion, it's the sun, it's the magnet, it's whatever, is in the center. And then at an equal distance, like if you say 100 meters, so 100 meters from whatever is in the center of this. So if this is a sphere, this is all the points that are 100 meters away. So if we say it's based on distance, every single point on the surface of this balloon is going to have the same strength or intensity or whatever of the thing we're talking about. The explosion will have spread. Let's forget about bouncing off the ground or anything. Let's just say it was in midair. The explosion will have spread, and all along the face of this 100-meter radius balloon will be the same strength of explosion energy in all directions. It will be the same intensity of light. It will be the same magnetic field strength. If we get closer, we have a smaller balloon to represent the thing is still in the middle, but we're a shorter distance away. So it's going to be stronger, more intense, or whatever. But the point is, you've got a center and a radius, and all these points are all the points that are the same distance from the center, so they're going to be the same strength, since we say it's based just on distance. And of course we can go the other way, and we can get further away. We can have a bigger balloon. So once again it's in the middle, and a greater distance, so all of these points, if we assume it's a sphere, are going to be at the same strength. A different strength from this one, but the same strength as each other. The surface area of a sphere is 4 times pi times the radius squared. 4 is a constant, pi is a constant, it's about 3.14-ish. The only thing that changes is radius here. This just scales it. So here's our square. Inverse square, as radius gets bigger, the strength gets smaller. That's the relation. So radius gets bigger, meaning we get further away from the center. Gets bigger by the square. So there's a square, and then it's inverse because as the radius is getting greater, the strength is getting lesser. So they call it inverse. So before I go into details about the 3 ways to visualize this, it's actually gets to the same point. It's 3 different paths all leading to the same point. But I have a physical illustration. Imagine that this, at the center of this balloon, is the Earth. And we're talking about gravity. So at the center of this balloon is the Earth. The surface of this balloon is the distance between the Earth and the Moon. And here is what's left of the Moon. Don't worry about that. I'm sure it'll be fine. So here is a circle, and I have traced this half of the Moon on this balloon, as you can see. And the idea here is, you can see we approximate the Moon as a point and the Earth as a point. In reality, if you're doing a perfectly accurate, absolute accuracy thing, you're going to do all kinds of surface and volume integrals, because the gravity of my feet is different than the gravity of my head because they're different distances from the Earth. But it's not that big a deal. The Earth and Moon are so far away from each other, this is not the scale obviously, that it doesn't matter. You can just treat them both as taking up a point in space. So the idea is, the Earth is at the center, the Moon is on the surface, the radius is the distance between them, and all the points on the whole surface are at equal strength, whatever that strength is. So now let's get further away. I have a bigger balloon. I traced the Moon on it when it was the same size as that balloon, and then I blew it up some more to say, hey, we've gotten further away. And now you should be able to see, hopefully, the difference isn't as stark as I would like, but can you see? There we go. Do you see how the circle is bigger? I actually traced this and then blew the balloon up a little more, and the circle got bigger. So the moon is occupying the same amount of surface area of the sphere, of the balloon, but when it blew it up, so it had a certain strength. The normal size balloon, there's a certain gravitation at this distance. That same amount of gravitation is in this circle. Exactly the same amount of energy is in both circles. But it's over a bigger area. The moon is not being touched by all of it. There's less interaction between the gravity and the moon. So it's a weaker force. See, there's empty space. The gravity that is in this outline here, this missing part, is not interacting with the moon in this example, and that's why the force is weaker. So everybody learns differently, and some of you thought that was a great explanation. Some of you didn't. So here's a different one. Let's take those 3 again. Let's start with radiation. Now I'm doing it on the board, so it'll be circles. Just pretend it's spheres. So let's say we have the sun. Here's the sun. Let me do it over here a little bit. So here's the sun, and here is the Earth. Not the scale, obviously. So shooting out from the sun, let's pretend it's a point. So we go like this, and we go like this, and you can see that there is an arc. Any photons that are shot at the Earth will hit the Earth. Any that go up this way and this way will not hit the Earth. It's only the ones that are shot at the Earth will hit the Earth. So they're shot at a certain rate, right? So into this cone, because it's a cone, right? Because 3 dimensions. So out of this cone, this arc, will be shot a certain number of particles on average per second, a certain number of photons. Take the same Earth, the same size, put it further away. So the Earth is moving. The same number of photons are coming out of this cone. It didn't do anything to the sun. The Earth moved further away. The Earth is the same size, but further out. Because of the angles, the cone is bigger. So it's the same rate of fire and the same spread of fire going at the Earth. But it's further away. It's not taking up the whole cone. So some of the ones that won't miss the Earth here will miss the Earth here. So that's why you have a lesser intensity a greater distance away. Similarly, if you move the Earth closer, same size, I'm not a draftsman, pretend it's the same size. Now, not only is the entire cone hitting the Earth, because it was here and we get closer, the cone is smaller. The entire cone is hitting the Earth, and now more that was outside that cone is also hitting the Earth. So we get closer, it becomes more intense. Because not only is it accepting that whole cone, it's accepting more. That's the easiest one. Now let's do expansion. Here are 2 effectively identical balloons. This one is not blown up and this one is blown up a lot. You may be able to tell from looking that even though they're the same color, this one is a lot more pale, this one looks a lot more creamy. They both have roughly the same number of molecules of rubber, latex, whatever they are. It's the same number of molecules, but the ones in here are spread out. There's a certain stretchiness to the bonds between them. Maybe they're folded and then they unfold, whatever it is. Also, if you hold this balloon up to the light, which you can't see, but if you hold it up to the light, it's blocked completely. But if I hold this up to the light, I can see the light through the balloon, whereas I can't see it through this, because again, there's gaps. It's the same material, the same amount of material per square inch, but it's spread out. That is expansion. As your shock wave expands, as your sound wave expands, as whatever physically expands in 3 dimensions in a sphere outward, as the surface area of the sphere gets bigger, you have the same amount of material, greater surface area, less material per surface area. So that's why things that expand get weaker with distance. They're literally spreading out, but nothing is being added. It's just spreading out. So that was also pretty easy. Now the fun one, force. And boy, do I have a mathematical treat for you. Now let me go back to these for a moment, where I have the moon at its normal distance from the Earth, and then we put it further away, and so the same force that was applied to the moon is spread over a greater surface area, so not all of it is interacting with the moon anymore. Basically, gravity is infinite. Magnetism is infinite. The gravitational attraction of the Earth and everything with mass extends everywhere throughout the entire universe, the entire observable universe. And at every radius, no matter how small or how big, from here to the moon or here to Alpha Centauri, there's roughly the same amount of total force being exerted at any particular radius. There's a certain amount of force being applied to every single point on this sphere put together, and the same amount of force being applied to every point on this sphere put together. The same amount. Similar to expansion, it's spread out. You could have 100 newtons per meter squared here and 50 newtons per meter squared here. We'll do some numbers in a moment, but that's the point, is you have the same amount but a greater surface area, so per surface area is smaller. So when you have the same size object, such as the moon, at a distance where it's more spread out, there's less interaction. The moon is comprising the same amount of surface area as it did before, but there's more surface area available, but there's not more force available, so it gets less force. It's math time. Gravitational force, like any force in the Newtonian world, is mutual. Earth attracts the moon attracts Earth. Don't worry about it. Let's take an Earth-centric view. It's just the same but negative. The force that the Earth exerts on the moon in newtons is given by the following formula. A gravitational constant times the mass of one times the mass of the other over the square of the distance between them. Hey, there's our inverse square. As the radius gets bigger, this square gets bigger, but it's dividing so it gets smaller. Inverse square. You'll see this all over the place. As a reminder, the Newton unit is kilogram meters per second squared. Don't worry about it. The gravitational constant is 6.67408 times 10 to the negative 11th meter cubed per kilogram second squared. Also, don't worry about it. It's just a number. I've already done out all the math. I'm not going to walk you through it. I'll just give you the numbers that took me 5 minutes to type in by hand. So here's the formula we're using to calculate. This is the one we're trusting. I know, Einstein's equations. We don't need them. Earth versus moon, we don't need Einstein's. Newton's is fine. So here's the equation. So this is the canonical result. This is the one we're going to say is absolutely true. The Earth is roughly 5.9 times 10 to the 24th kilograms heavy, and roughly 6.3 times 10 to the 6 kilometers radius. The moon is roughly 7.3 squeak times 10 to the 22 kilograms, and 1.7 times 10 to the 6 kilometers in radius. We're actually pretty surprisingly close. The trick is we're pretty far apart. The distance between the two is roughly... Oh, I screwed up. These are meters. Sorry. Somebody was already screaming at the screen. Relax. That's meters. They're roughly apart 3.8 times 10 to the 8 meters apart. So that's the scale we're working with in meters. So I calculate the gravitational attraction using the Newton formula, and I get roughly 1.9 times 10 to the 20 newtons. That's roughly the attraction from the Earth to the moon right now. So now we're on this one. The one where it fits just right. This is the normal distance to the moon. The surface area of that sphere, the entire sphere at that distance from the Earth, is roughly 1.8 times 10 to the 18th meters squared. So that's the entire balloon. But how much surface area is just the moon taking up? Well, let's do an approximation, because we're dealing with, 10 to the 6th meters? Let's take the moon and let's squash it down to basically a circle that's only 100 meters thick. 100 meters thick is pretty thick, but not on an astrophysical scale. 100 meters thick compared to the distance between the Earth and the moon is nothing. So let's just say it's just going to be, if we have our little, it's just a rectangle like this, and it's going to be 100 meters thick, and I'm going to spread the volume of the moon just into a platter, basically a cylinder, 100 meters thick. The volume of the moon is roughly 2.1 times 10 to the 19th meters cubed. Divide by 100 meters, and we obviously get 10 to the 17th meters squared. So 2.1 times 10 to the 17th meters squared is roughly the surface area of this shell, 10 to the 18th meters squared, that just the moon is taking up. So we know how much force, and we know how much surface area. So we want to have force per surface area. And as it turns out, that ends up being about 902 newtons per square meter. That number got smaller all of a sudden, didn't it? But there's a lot of square meters here. 902 newtons per square meter. So on this smaller circle, where the moon perfectly fits, every single point on this sphere, quote unquote, is getting 902 newtons per meter squared. So what is the total energy, the total force rather, being spread? Well, now, this is per meter squared, so we want to times meter squared. We want to multiply, but now we want to use the entire shell. We calculated this using just the surface area the moon is occupying based on the force being exerted on the moon. Now, if we multiply by the surface area of the whole sphere, which is at the distance the moon is at, we get roughly 1.6 times 10 to the 21 Newton. And there's our big number we were looking for. 1.6 times 10 to the 21 Newton in the whole balloon, spread over the surface area, 902 newtons per meter squared. So if I take the bigger balloon where the moon is smaller than the circle now, that same amount of energy, 902 newtons per meter squared over how many meters squared, and now we spread the same amount of newtons, the same amount of force, into a bigger area, even though the moon is not taking up a bigger area. That same 1.6 times 10 to the 21 newtons is spread across the whole surface of this balloon. Same force spread across the whole surface, but there's more surface here. Let's double the distance. Let's just say the moon is double the distance it was away. So now, everything's the same except the moon is now 7.6 times 10 to the 8 meters away. We just doubled the distance. That's all we did. So what we're expecting, inverse square. So if we doubled the radius, we should expect 1 over the square of 2 equals 1 over 4. So we should expect 1/4 of the force at double the distance. That's inverse square. So we take the same total energy, the 1.6 times 10 to the 21 newtons, and again, now we want meter squared. So 1.6 times 10 to the 21 newtons, and we want newtons per meter squared. The new area, the new surface area of the bigger balloon is roughly 7.4 times 10 to the 18th meters squared. So now we're getting newtons per meter squared. And that equals about 225 newtons per meter squared. That's roughly a quarter. 225 to 450 to 900. The previous number was 902. That's about a quarter. That's what we're expecting. But we still need to check our work. So we have about 225 newtons per meter squared less force per surface area because it's the same total force and a greater total surface area. So we take the same surface area of the moon, the 100 meter thick smushed down version, looks like a hockey puck. So 225 newtons per meter squared times, and now we want meter squared, which was 2.1 times 10 to the 17th meter squared, which roughly gives us 4.9 times 10 to the 19th newtons. So before we had 1.9 times 10 to the 20 newtons. Now we have 4.9 times 10 to the 19th newtons at double the distance. Roughly a quarter. Seems good. I trust my calculator. Well, let's write that again. 4.9 times 10 to the 19th newtons at double the distance upon the moon from the Earth. Then we just take that equation, Newton's equation, the one we trust, the authoritative answer, and what do I get? When I just simply double the radius and plug it right in with the gravitational constant and everything. 4.9 times 10 to the 19th newtons. That is inverse square for forces. There is a total amount of force due to gravity being exerted upon both of the surface areas of these balloons. The smaller one and the bigger one, same amount, but spread. If you take however many newtons, what was it? 1.6 times 10 to the 21-ish newtons, and you go out to the edge of the observable universe. It's that many newtons at the edge of the observable universe. But the surface area there is really big. So even though it's the same number of newtons as you get right at the moon and the edge of the observable universe, we are not exerting that much force on things that far out because it's just dilute so much. It's even homeopathy is strong compared to that. That's the trick. Forces do not diminish at any distance. They spread. They spread by spheres. That is inverse square. That's why everything that expands in 3 dimensions outward, be it forces, be it explosions, be it photons being fired out, for different reasons. The cone of fire and how much of that cone of fire your target is occupying, or how much spread there is in the physical thing that's moving outward, or how much surface area that force is being stretched across. 3 completely different mechanisms, one actual thing. Inverse square. I love it when physical principles come together. And while I run for my life from good old Hannibal, I'll be seeing you.